Example 1. Determine the shear stress at the centroid as well as the values of shear stress at point H and K shown in the figure. So if the section is subjected to a shear force of V equals 145 kilonewton. Okay, so first of all, you need to determine the I and Y bar, right? Since anyway, to calculate the shear stress, you need to use this equation tau equals VQ over IT, or tau equals Q over T. Right? You need to use either one of these two equations. But first of all, you need to determine this I value. Then based on the Y bar, you calculate the D values so that you can calculate Q. Right? So first of all, the first step will be determine the centroid and the moment of inertia. So I will skip this step and directly give you the result of calculation, since you're supposed to know how to calculate these two values. Okay, so here the I is 72.6 million millimeter to the fourth, and the Y bar is 121.5 millimeter from the bottom. Okay, this is from the bottom here to here. This is Y bar equals 121.5. And based on this result, we can calculate the shear stresses at the three different points. Okay, first of all, let's look at the centroid. So at the centroid, we need to calculate the Q values first of all. Right, the Q equals a sum of AD, right? And here this is the case which we use to calculate the shear stress at the centroid. Okay, since we already know that the Y bar equals 121.5, and this will be the area, the purple colored area will be the area we'll consider to calculate the Q. Well, you need to divide it into two sub areas, and sub area 1 and sub area 2. Okay. So this equation can be extended as A1 D1 plus A2 D2. Right. So A1, first of all, let's look at A1. A1 here. So the thickness is 8, right? So you just need to consider, you need to determine the dimension here. Okay, and so this can be calculated as 121.5 minus the thickness of the bottom flange, that is 20, right? Minus 20 by 8. Okay, so this is A1. Here what we determined is A1. Then you need to multiply D1. So what's D1 in this case? The D1 is the distance from the global centroid to the local centroid. Okay, so that is 121.5 minus 20 over 2. Right, it's a half of the vertical dimension of this square, of this rectangle. Okay, so here, this is the D1. Then plus A2, okay, the area of the sub area number 2. So that is relatively easy. You just got 20 times 110. Okay, as we already have this dimension, this dimension. So this is the area A2, okay, times D2. So what is D2? The D2 here is just 121.5, the y bar, minus half of the thickness of the bottom flange, right? That is 20/2. Okay. Here you got your D2. Then here we got a result of the Q. The Q is 286,500. Okay, cubic millimeter. We also need to consider the thickness T at this point, and as indicated here, right, the thickness T is just 8 millimeter. So we can calculate the tau at this point. That will be VQ over IT. V is 145 kilonewton, right? Kilo by 286,500 over the I. We determined the 72.6 million. 72.6 million and times 8. Okay, so we got 71.5 MPa. Okay, here the units is just like, here you get a Newton, millimeter, or in Newton millimeter, so you get a MPa, right? Then step 2, let's analyze point H. Okay. At point H, let's look at here. Okay. Look at here. At the point H here, if you cut it, you get a area above point H. It's a T-shaped beam, T-shaped area. So again, you need to divide it into 2 sub areas. You get a area 1 and area 2. Okay. Again, the Q will be calculated as A1 D1 plus A2 D2. And the A1 will be, look at here, the dimensions was 70 by 15. 70 by 15, this is the A1. Times D1. So the D1 would be, first of all, 300 minus y bar, the overall height 300 minus y bar 121.5, then minus half of the thickness of the top flange, that is 15/2. Right, so this is D2, D1. So let's look at A2. Well, the A2 here, right, will be (75 minus 15), since here from the top to the H is 75. Right, you got a 75 minus the thickness of the top flange, 15, times 8. Okay, this is the A2. And D2 will be from the global centroid to the local centroid, so that will be 300 minus y bar, then minus 15, this is the thickness of the top flange, then minus half of the height of the sub area, so that is 75 minus 15/2. Okay, so this is D2. Okay, to summarize it, we got a 243,630 cubic millimeter. And the T value here at this point, again, this is still 8 millimeter. So using the equation here, the QH, so the shear at point H, shear stress at the point H will be VQ over IT. I got 145,000 times 243,630 over the I 70. $72.6 million times 8. So you will get 60.8 MPa. Okay, the last step, let's look at point K. Okay, the point K will be relatively easy since it's just here. The point K is here. Right, so you cut it, you get a small area as shown there. So the QK, you will have only one area, so that is just AD. Right, the A is just 20 times 21. Okay, hence the dimension here is 21, the thickness is 20. Okay, so the D value will be 121.5 minus half of the thickness, right, 20 over 2. So you got 46,830 cubic millimeter, and the thickness here is 20, as denoted here. It's the thickness of the bottom flange. So here it's 20 millimeter, so not 8 anymore. So in the end, the shear stress at point K is just VQ over IT. You got 145,000 times 46,830 over 72.6 million times 20. Okay, the result will be 4.68 MPa. Okay, so this is our example 1. So then here is the summary. What is shown here is the I-shaped beam, thin walled beam section. Is the cross section. Okay, you can see that you can calculate the stress, the shear stress at random points, and you can also calculate the shear flow at the random points. If you summarize a lot of calculations, you will get this result here. Okay, on the top flange or the bottom flange, the Q equals 0 on the end point, then it will keep increasing to the middle of the flange where you get the local maximum values of Q. Right? So this is the distribution of the shear flow along the top or bottom flanges. And then along the web, you can see that the Q values will start from a minimum value and then keep increasing towards the centroid. Right? Towards the centroid. Then it will achieve the global maximum value Q at the centroid. Okay, those are the distributions of the Q. And if you want to calculate the forces, as shown here, you will have this flows, the flows too. Okay, the flows along the flanges and the web. And this slide is very important, as I added the star sign here. Okay, the star sign here means that it's very important. You can see we have analyze the T-shaped and I-shaped areas, cross sections, then you have know that how to calculate the shear stress or shear flow at these points. Okay, how to cut and get the area, and how to consider the thickness. Right, you just consider one area or composite area and consider the local thickness of T. Right, and also in the T-shaped beams, you also know how to cut areas and determine the local thickness. Cut the composite areas and consider the local thickness, right? But in some other shapes, as shown here, if you have a hollow core box or a C-shaped sections, then how to consider the area and thickness. This is summarized here. This is how you cut. If you are requested to calculate the shear at this point, or at this type of point, you need to do this kind of cutting and consider the area of the blue-shaped area. Okay, based on this area, you calculate the Q. Then when you calculate the stress, you need to consider 2 times T. Okay, 2 times T, not just 1 T. Okay, the T is just here. Right, this is the T value, and here this is the T value, but you need to consider 2 times T. Okay. So knowing that to solve the shear stress in thin wall members, you just need to follow these 4 steps and determine. Step 1 is determine the shear force at the required section. Step 2, determine the centroid and the moment of inertia. Those are the regular steps. Then step 3, you cut the section perpendicular. This is important, right? Cut the section perpendicular to the direction of a shear. To the direction of the shear. Then determine the moment of area, the Q, and the thickness there. Then you use the general equation to calculate the shear stress. Then we'll have a couple of more examples to denote, to illustrate how to calculate the stress using the equations and the steps for different beam sections, different shapes of cross sections.